Welcome to the first episode of the AI for Business course, your ultimate non-technical guide to understanding AI and how to apply it in the real world. If you're not an AI expert, but you truly wish to comprehend what it is and how to utilize it in your work, this course will definitely assist you in achieving that. If you haven't watched the course intro, I recommend you do so through this link. My name is Omar. I've been helping many organizations all over the world apply machine learning to transform their day-to-day operations, and today, we'll dive into what AI is and how it works. This episode consists of three main parts. First, we'll start with a high-level overview of AI, machine learning, and deep learning. Next, we'll focus on machine learning, the most influential form of AI today. We'll explore its various types, how each work, and have a look at some use cases. And lastly, we'll delve into deep learning and take a look at some of the applications it's enabling today. You might be wondering, do I really need to know all these details? The truth is, having a foundational understanding of AI is crucial to make the most out of it, even if you're not going to be the one building it or writing code. This knowledge equips you with the ability to understand which solutions are feasible and which are not, communicate and collaborate with AI teams, and set the right expectations with management and stakeholders. As promised, we're not going to delve too deep in the weeds, just explaining the key concepts. So let's dive right in. AI, or artificial intelligence, is the science of enabling computers to achieve human-like levels of intelligence. This is accomplished by replicating the qualities of the human mind, such as perception, reasoning, planning, and decision-making. Machine learning is a subfield of AI that enables computers to learn from data by discovering and extracting patterns, as opposed to being explicitly programmed. While AI encompasses other fields, machine learning is by far currently the most impactful and powerful. So consequently, when people refer to AI today, especially in industrial context, they are usually referring to machine learning. Deep learning is a technique within machine learning that is inspired by the structure of our brains. It has recently excelled at identifying patterns and learning from highly unstructured data, such as images, voice, and text. AI is empowering a wide range of applications, such as ChatGPT and Midjourney, virtual assistants like Siri and Alexa, personalized recommendations for Netflix and Spotify, email spam filters, fraud detection systems, language translation tools such as Google Translate, and more. Each of these applications employs machine learning at its core. Intrigued? Let's have a closer look at machine learning and how it works. There are four major types of machine learning: supervised, unsupervised, self-supervised, and reinforcement learning. Many of the AI applications used in production today leverage the first type, supervised learning, which is learning how to make predictions based on examples. These examples should map certain inputs to some output that we're trying to predict. The more input-output examples we show to the machine, the more accurate its predictions gonna be for newer inputs that it hasn't seen before. Let's say we're trying to predict house pricing. The inputs could include square footage, number of floors, number of rooms, whether the house has a backyard or not, etc. The output could be the actual house price. If we can get such data for thousands of houses, we can use it to teach a model how to predict the pricing of new houses that it hasn't seen before, provided we have the input attributes of those houses. In supervised learning, the process of teaching a model using input-output examples is called training. During training, the model tries to find the underlying patterns between the inputs and the output, and learns how to make predictions based on these patterns. The output that comes with the training dataset is called a label. So, a training dataset with the inputs and corresponding outputs is called a labeled dataset. We use labeled datasets to train models to make predictions. Let's take another example for supervised learning: email spam detection. The training data in that case could include inputs like the sender's email, the time the email was sent, the content of the email, and the email subject line. And the output could be an attribute dictating whether each email is classified as spam or not. In the house pricing example, we were trying to predict a quantity, the house price, using a technique called regression. In the email spam detection example, we were trying to predict a probability, spam or not spam, using another technique called classification. Supervised learning could leverage either regression or classification depending on what are we trying to predict. Supervised learning could also be used with other types of data. We can use it, for example, to train a model to detect whether an image has a dog or not by showing it different images, some with dogs, others with no dogs. You can use it to train a model to detect sentiment in tweets, whether it's positive, negative, or neutral. If you show it a lot of examples of tweets with positive, neutral, or negative sentiment, the examples are endless. Unsupervised learning is another form of machine learning that does not rely on labeled data. Instead, it deals with inputs only, and its goal is to find patterns, relationships, or structures within the input data without any guidance from output labels. One of the most common techniques in unsupervised learning is clustering. Clustering groups data points with similar attributes, allowing them to be assigned to distinct clusters. This could be particularly useful for applications like customer segmentation, where understanding distinct customer groups could be very important for businesses to help them come up with better targeted marketing campaigns, for example, or improve their product offerings. Anomaly detection is another application of unsupervised learning, which aims at identifying data points that deviate significantly from the norm. It could be particularly useful for applications like financial fraud detection or cybersecurity threat detection, and so on. In summary, unsupervised learning can help you uncover hidden patterns and relationships in your data without the need for labeled examples. I'm sure by now you have heard about ChatGPT and probably Midjourney, both of which are prime examples of generative AI applications. Those two utilize an emerging category of machine learning called self-supervised learning, which combines aspects of both supervised and unsupervised learning. In self-supervised learning, the model generates its own labels from the input data, which could then be used to train the model further, similar to supervised learning. The primary advantage of this approach is that it almost eliminates the need for large amounts of labels, which is usually a time-consuming process and costly to obtain. ChatGPT is a large language model that generates human-like text by predicting the next word in a sentence or a conversation based on the context of the words that came before. In this approach, the model treats the task of predicting the next word as a self-supervised learning goal. Each next word in the provided dataset acts as a label for the preceding sequence of words. This process allows ChatGPT to learn from large amount of unlabeled text, enabling it to provide coherent and contextually appropriate responses in a conversational setting. Another exciting development in self-supervised learning is the use of diffusion models, which are capable of generating images from textual input. Those models, such as DALL-E 2 and Stable Diffusion, are able to take text input, such as the description of a scene, and generate corresponding images. The fourth and last type of machine learning we're going to explore today is reinforcement learning. This type focuses on learning by interacting with an environment, optimizing a set of actions to achieve the highest possible outcome or reward. In reinforcement learning, an agent takes actions within an environment to achieve a specific goal. The agent receives feedback in the form of reward or penalties for each action it takes, allowing it to learn and adapt its strategy over time. This trial and error approach enables the agent to discover the optimal sequence of actions that lead to the highest cumulative reward, effectively learning from its experiences. Reinforcement learning has found success in numerous real-world applications, including supply chain logistics optimization, robotics navigation, and optimizing trading strategies. It has also shown great promise in the field of autonomous vehicles and game playing, where agents need to make complex decisions based on dynamic environments. So, to wrap up this part, we have discussed four main types of machine learning. First, supervised learning, which uses labeled data to make predictions. Second, unsupervised learning, which can help us find hidden patterns and relationships within our unlabeled data. Third, self-supervised learning, which combines aspects of both supervised and unsupervised learning and uses the data itself to generate labels. And finally, reinforcement learning, which focuses on learning the best policies, actions, and decisions based on interacting with an environment. Those different types provide a powerful toolkit for addressing numerous real-world challenges and help enable AI-driven solutions. Now that we've explored different types of machine learning, let's dive into deep learning, which has been a driving force behind many of the recent AI breakthroughs. Deep learning is a subfield of machine learning that focuses on algorithms inspired by the structure and function of the human brain, specifically neural networks. These neural networks consist of layers of interconnected nodes or neurons that process and transmit information. The depth of a neural network, meaning the number of layers it has, is what differentiates deep learning from traditional machine learning techniques. The true power of deep learning lies in its ability to automatically learn complex representations and hierarchical features from vast amounts of data. This capability is especially beneficial when dealing with high-dimensional and unstructured data such as images, voice, and text. In a deep learning model, the input data is processed through multiple layers of neurons, with each layer learning progressively more abstract features. The final output layer provides the result, such as a prediction or classification. During training, the model adjusts the weights of the connections between neurons to minimize the error between its predictions and the actual outcomes. For example, in image recognition, a deep learning model might first learn to identify edges and textures in the lower layers, then shapes and objects in middle layers, and finally, more abstract concepts like specific object categories in higher layers. For instance, it can differentiate between a Labrador and a Bulldog in dog images, or an SUV from a sedan in car images. Some popular deep learning architectures include convolutional neural networks, or CNNs, which are usually used for image recognition tasks, long short-term memory networks, or LSTMs, which are uniquely suited for modeling sequential data like time series forecasting, and transformers, which have become fundamental in advanced natural language processing tasks, driving the success of models like GPT for text generation and also being adapted for computer vision tasks. Deep learning has become the go-to method for most modern applications that process and extract insights from highly unstructured data. For example, Siri employs deep learning for speech recognition. ChatGPT, Midjourney, and DALL-E 2, they all use deep learning for content generation for text and images. And in computer vision, deep learning has enabled a whole new level of object detection and image classification systems, enabling applications like self-driving cars, autonomous robots, and autonomous drones. With this knowledge in hand, it's time to wrap up today's episode. I hope you find this introduction to AI insightful and valuable. Now that you have a good understanding of the core concepts, it's time to ask a crucial question. What are the practical use cases that can make a real difference in your work today? That's exactly what we're going to explore in the next episode. We'll dive into the major AI use case patterns that apply across different industries. We'll also explore a lot of use cases in different sectors, such as manufacturing, supply chain, healthcare, retail, banking, insurance, government, and more. If you enjoyed this video, I appreciate if you can share it with others who can benefit from it and give it a thumbs up if you want. If you want to see more content like that, you can subscribe to the channel. And until we meet again, thank you for your time, and very much looking forward to seeing you in the next episode.